Okay, thank you for coming back. I'm now going to explain another method. My mouse. Okay, which is called minimal error pruning. The previous one was called reduced error pruning, sometimes also abbreviated as REP. REP, REP, reduced error pruning, and this one is abbreviated as MAP. And you can see it. Some of the authors are here. I had the pleasure of contributing to the invention of this method, which was a real joy at that time. Now the point of this method is that it does not require a pruning set for estimating error. So it's useful in the cases when we have shortage of data. It estimates error on new data directly from the growing set using the Bayesian method for probability estimation. And one possible estimate is called Laplace estimate. Another one is more sophisticated, is called M estimate. And if you remember, when I played with orange, there was parameter M there playing a most important role. This is this M here that comes from probability estimate. The main principle is to prune so that the estimated classification error is minimal. So to minimize classification error. But REP also does the same thing. It wants to minimize classification error. The only difference is that REP uses independent pruning set for estimating errors, whereas here we estimate errors directly from the data that we have in the pruning set, in the growing set. Okay, so this is the situation then. We have to decide about pruning at node V. This is part of our tree, rooted at V. Maybe there is some subtree also existing up there. But the tree has subtrees. The P1, P2 are probabilities of going to these subtrees. And now let us denote as E of t the error of optimally pruned tree T. So what does that mean? This whole thing is tree T. And then we start by working on the subtrees. We prune T1. We decide that this is the best way of pruning T1. We prune T2. Maybe this is the best way of pruning T2. And then when we combine all these pruned subtrees together, then we get optimally pruned tree T. And E of t, this optimally pruned tree T, will have error E of t. And then the other thing, okay, I'll move back here. So this is the best pruned subtrees, and now we also need to look at the root V. How well can we classify at the root V, which would happen if we pruned the tree just under the node V. So this is why we are interested also in the accuracy here, and we will denote the error at node V as lowercase e of V. And now obviously what is the decision whether to prune or not? We just need to compare these two, E of V and E of t. And if this is smaller than that, then we decide to prune here. Then in that way we'll get we will minimize the error of the resulting pruned tree. Okay, so that's the basic idea. Now, just a few maybe subtleties here. The error at node V is the probability of class of an example not being equal to C, where C is the majority class at node V. The overall error of all these subtrees that we said is E of t. That is the weighted sum of the errors of the pruned subtrees. So that's the weighted sum E1 E of t1 plus P2 E of t2 and so on. So that's the overall error of the optimally pruned subtree. Okay, and now the error about the decision about pruning is reduced to this. We want to minimize the error, and now the candidates are either we prune just under V, in which case we get that much error, or if we don't prune there, the error will be this much, and this decision will produce the minimum of these two errors, which then also becomes the error of the optimally pruning of this whole subtree. Okay, that's the principle, and I think this is all pretty straightforward. But there's something which is not so straightforward. Can anybody see what is not? I have not explained to you something in this schema, and that is very crucial. What's that? Sorry? Which one? EV. Exactly. So, right, exactly. That is the big question. You see, how we don't know this one, and we may have some ideas how to do that, but we don't have any very reliable and easy way of doing that. In REP, in reduced error pruning, we use the pruning set to do that. But here, well, we say we are not going to use pruning set. We need to do something else. Okay, here are some answers. How to estimate the static error EV? We may use Laplace estimate or M estimate or probability, possibly something else, but these two are quite all right. And we have this situation. At this node V, we have altogether capital N examples, and NC is the number of majority class examples. So if the majority class is C, then we go obviously, one obvious decision is to classify everything into class C, the majority class. And what is the error? Now, okay, I can tell you what you may, what 90%, 99% of the people will propose. They will say that the probability of error at this node is equal to okay, I will do it the other way around. The probability of correct classification is just the number of majority class divided by the number of all examples that fall into this leaf. Yeah? In that many examples, cases will get the correct classification, and this is the number of all the cases. What do you think? Would you do the same? I mean, all people tell me exactly this formula. Always. Maybe some of you read a little bit my slides, so you may already have some suspicion about that. And since I'm spending so much time, you already suspect. But anyway, this is the most natural, and this would not work. If you did that, that would not produce any useful pruning. So we need to do something else. And the answer is we use Laplace or M estimate. By the way, this also is when we talk about small samples, and typically here we have N would be how many? Maybe 1 or 2 or 3 or 4. So we are talking about small samples. In those cases, this is not a good formula to use. This is very, very, very wrong, which I will show a bit later. Now the Laplace estimate is this one. The probability of class C is not just, well, in the naive formula, the one that everybody uses is nc over n. But in Laplace we have something added, nc plus 1 over n plus k, where k is the number of all class values. Okay. So suppose that nc equals 1 and n equals 1. We have a node with just one example in this node. According to this naive estimate, the accuracy of this example will be at this node will be equal 1. Yeah? So that will be equal 1. According to Laplace, I will just put PL for Laplace. What will that be? It will be 1 plus, according to formula, 1 over n is 1 plus 2. It can be 2 if we have two classes, two possible values. We could also have more. But suppose that we just have two classes, crosses and circles, so this will be 2/3. So it's 2/3 and it's not 1. I will later show why this is better than straightforward relative frequency. So why is this better than just this red part of it? But still, Laplace has some theoretical problems. It assumes that all classes a priori are equally likely, which usually is not the case. And the degree of pruning will depend on the number of classes if you use this formula in this way. So a better formula is this M estimate. The format of this formula is a little different, I think, in your notes. In the meantime, I found a nicer format for this formula. But anyway, this is a little more sophisticated. It says the following. It's PA times M plus N. N is the number of positive examples. N is again the number of all examples. M appears here and PA appears here in addition to other things. Now PA is the a priori probability of that class. So if we have some prior expectation about that class, then we will, in this formula, we will tell what our prior expectation is before we have seen any examples. For example, and I can tell you how this idea of prior expectation actually comes about. Suppose that you are throwing a dice, and the result is 1, 2, 3, up to 6 points, and you are interested in the probability for a particular dice of showing 6 points. So what would your immediate reaction would be? What is this probability? It's 1 over 6. This is your prior belief because you know something about the geometry of the dice, and normally you would say, well, if this is a proper dice, it has probability 1 over 6 to show 6 points. So this is your prior PA. That would be PA, a priori probability. Then later you may start some experiments with this dice. You throw it 10 times, and each of these 10 times it showed 6 points. And then now you may become a bit suspicious. Is this a proper, honest dice? Maybe it is weighted in some way so that it is biased towards showing it likes 6 more than other honest dices. And then you would gradually modify the probability of 6 for this particular dice, and you would use in this modification you may use this formula. And m is a parameter of the formula which is greater or equal to 0. It can be even infinity. Now you see if m is equal to 0, then this estimate is reduced to simple relative frequency, n over n. But for other values of m, then we get different behavior. And for m equal infinity, what will be the estimate equal to? It's just PA, that's right. So you see, we can with m we can attribute more weight to our prior probability. So in the extreme case, when we are so sure about this prior probability, suppose that we are playing with this dice, it is showing some funny behavior, but we believe so strongly that this is an honest dice, we will we will set m equal very high so that it will stay equal to 1 over 6 all the time. Okay, so anyway, this parameter m is tuned by an expert. The expert who understands the domain is best qualified to say how shall we choose this parameter m. Okay, there are some important points here. We can usually vary m in tree pruning, exactly as I was doing with orange. I was changing m and looking for the best value of m, which would be most appropriate to the level of noise in that data. So I can adjust the pruning when I use m estimate. In tree pruning, I can adjust the pruning to the level of noise by varying m, and the most appropriate value for m will show the highest accuracy resulting from the pruned tree using that particular m. Now the choice of m is really something that is hard to say. If you have that much noise, you should set m to be equal 3.5. It never works like that. It is also very sensitive to statistical fluctuations, but we only have very rough guidelines. If we have low noise in the data, so the expert will say, I trust the data a lot, therefore my estimate of the noise is low, then I will set m low, and the result will be little pruning, which somehow is appropriate. If you trust your data, you don't want to prune a lot. If there's high noise in the data, the appropriate value for m is high, and that will cause much pruning, which again is appropriate, because with pruning we get rid of noise as well. Okay, so that's the basic about using m estimate. As I said, there are many other techniques for pruning. Here I have just 3 of them mentioned, and there's this error complexity pruning of a very famous method by Brahman and his colleagues in '84. So that is implemented in the program CART. Probably some of you have heard of CART, which is now included into statistical package S+. Has anybody heard of CART? No. Okay, did not appear in this course. But anyway, it is a very classical system. You can see very surprisingly, 1984 is the year when Brahman and his co-authors, Friedman, Olshan, and Stone, actually already published a book on learning classification trees. They call them classification trees, not decision trees. They are statisticians, so that terminology was completely different from our terminology, but the ideas were very similar. And when we were developing, the AI branch of machine learning, we were struggling through our initial ideas and methods of pruning and evaluating attributes. Those people, the statisticians, were also in parallel working on this already probably for about 5 years. But nobody was aware of each other. I mean, the statistical community was not aware of anything going on in AI, and AI was not aware of this statistical community doing anything in machine learning. And I remember once I went on a conference and I gave a talk about tree pruning in, I think, 86. And fortunately, in that audience, there were some mathematicians, and there was this mathematician who said, well, this is very interesting. Now that I'm listening to you, it is like reading Brahman's book, chapter 2. And 5 minutes ago, you were talking Brahman's book, chapter 6. So it is, then I said, well, how is that possible? We don't know anything about that book. And he said, well, we also don't know anything about your work, but it looks very similar. Then I immediately went to, that was in Oxford, or Cambridge, I think. I went to a bookshop, I bought Brahman's book, and I said, true that these people in parallel invented all these ideas with a completely different terminology. But anyway, this is a very famous method of pruning. It is also pretty complicated. I don't think we have enough time to go through it, but it does. It tries to minimize this quantity here, the total cost, which consists of error cost. So that is the classification cost of the tree, and complexity cost. So that they want to penalize the size of the tree, which is the right thing to do in terms of Occam's razor principle and MDL. So intuitively they got all these right ideas, and also they wanted to penalize the errors that the tree makes on the learning data. And I said, well, this is a bit complicated, so I think I'll just skip it. It's even more complicated than necessary. So with further sophistication, they made this method actually perform worse than a simpler version would have. But anyway, it's still used in this cart system, which is still very popular. Okay, so I'm going to skip a lot of this. But I thought it would be nice to put all that also, because this is a kind of discovery that came in parallel from another field. Later Brahman also learned about AI developments, and from then on we keep meeting in machine learning conferences with Brahman, and he shows admiration for our work, and mutually we show admiration for his work. You learned about random forests in this course, yes? So, okay, you can see that Brahman became more part of machine learning community. Okay, there was a big comparison of various pruning methods in this famous paper by your supervisor, Donato Malerba, and Floriana Esposito is Donato Malerba's supervisor, and so on. Okay, so that we are talking about 3 generations now already. But anyway, that's a very good paper. I recommend to everybody who wants to learn more about this. Now, here I have a question for you. Now let me read this question, because it's a kind of apparent contradiction. Is there any lecturer in this school also here? No. Okay, I would, if there was, I would allow also lecturers to participate, because I think the question is sufficiently difficult also for the lecturers. The lesson from tree learning that I have been telling, and you all agreed, is as follows. Small trees are good, but not too small, You know that Einstein is known by the saying, things should be made as simple as possible, but not simpler. Okay, when you over prune, then it gets too simple. So, but generally, small trees are good. So simplicity is good because it enables high accuracy. Through simplifying, we get better prediction accuracy. Okay, do you agree with that? I mean, so far I have been only talking about this, and you all agreed with that. On the other hand, you had a lesson from ensemble classifiers, like bagging and boosting and random forests. You had that, when was that? On Friday, maybe? Or Saturday? So was that good? A pretty interesting idea. And then ensemble classifiers attain higher accuracy than single classifiers. I mean, that was the point. So the conclusion from this work is that complexity is good because it enables high accuracy. So so here we have simplicity is good, and here we have complexity is good, because they both enable high accuracy, which looks to me like a kind of contradiction. And if you haven't been aware of it so far, maybe can you try to explain it now? So maybe it's either Dr. Robnik Shikonia was lying to you on Saturday, or maybe I'm lying to you today. I would be very interested in knowing a good answer. Maybe it depends on data. Okay, that would be one possible answer. So what kind of data would be useful for, would be good for trees, and what would be good for ensemble classifiers?
Ensemble classifiers use simpler sample classifiers too. If you use a complex classifier, you don't get high accuracy, and you need simpler also, but combine different simple classifiers.
Okay, so there is also some simplicity in ensemble classifiers, because they use in turn simple classifiers as the basic classifiers. Okay, that's one try.
I think they both reduce variability in the trees. It's like in the first case they reduce variability by pruning, and in the second case it's not really necessary to prune, but you reduce variability to averaging over the prune.
Okay, I like this answer the best. This is also my speculation that in both cases there is a kind of tendency to simplicity, and the simplicity is done through averaging in the case of ensembles because of this voting. So although the whole structure, the whole ensemble of classifying is complicated, even with apologies to you, you pointed out that they may be simple, the members are, individual members are simple, but the whole thing is can be enormous, so it doesn't look like simple at all. But then the simplification step is when they are used to in classification. They only are allowed to vote, and then through voting we get this averaging effect. Which is a kind of simplification, and it's a different one from a simplification along a different dimension than in the decision trees, yeah. But it is a kind of simplification, and in decision trees we have again simplification of slightly different kind. And as you said, maybe there could be data set properties identified, which would show which kind of simplification is more appropriate for what type of data. But sometimes somehow this question occurred to me about 2 weeks ago in a lab discussion, and I asked everybody what people thought, and everybody said, well, interesting question. We have not really read much about how to answer this, but probably this is a kind of very likely answer. All right. Now, just a word about rule learning. You had a lecture on rule learning. You know that rules can also be overfitting. So, obviously, a good idea is to simplify rules. And ideas for pruning decision trees can be adapted to learning if-then rules. So, pruning, which means that we then prune rules. Also using, for example, reduced error pruning, REP, applies to pruning rules and so on. There are some technical complications because it turns out that it is more difficult to prune rules than trees because of the structure of trees. That is a kind of simplifying circumstance. And there is a very good paper by our colleague, popularly called Yuffie, and his name is Johannes Fulmkrantz, 1997, in Machine Learning Journal. He published a good paper about techniques of pruning rules. Okay, so now the next thing is we saw this question of estimating probabilities from small samples. So I would like to say a few words about that. And I believe you. In this course, you didn't have any lecture to cover this particular question. If I'm mistaken, then please interrupt me immediately. Okay. Now the question is formulated as follows. Suppose I will first show an application. Suppose we have two classes, crosses and circles, and we have a leaf of the tree with two crosses, one circle in this leaf, and we would like to know what is the probability of cross in this leaf. And then, as we said, many people will say it is 2/3. But then I already said that this is very risky statement because we have such a small sample. We just have 3 cases, 3 examples in this set. So generally, the setting is as follows. The theoretical setting is we have done n experiments. That would mean n examples. And we can each experiment can give a positive or negative outcome. So there have been R successes in this sequence of experiments and S failures, and n equals R plus S. Now the question is how likely it is that the next experiment will be a success. Now the popular estimate of this probability is by relative frequency, which is it will be R over n, the number of successes over the number of all trials until now. But that's the one that we call relative frequency, or sometimes we call it naive estimate. Now this is okay if n is large, but for our cases when n is 3, this is not okay. And I will just give you the feeling of why this is not okay. I would like you to consider 2 situations. Well, first of all, one very obvious. Suppose you have a coin. You flip the coin, and you observe whether it showed the head, and you would like to determine the probability of the head. And we all know, okay, this is approximately 1/2, or probably exactly 1/2, should be 1/2 exactly. But suppose you make one experiment. I will write capital N equals 1, and there was one success. So it showed the head. Now, using relative frequency, this will say that the probability of head is 1. What do you think? So you say, well, this is completely crazy. Now, it's not only not only crazy in terms of our background knowledge. We are expecting 1/2, but also if we expect anything, not just 0 or 1. Here, with just one experiment, we cannot get anything but 0 or 1, nothing in between. So this is why there's obviously something wrong with that. Okay, but then let's look at coins further. Suppose we have now I'm going to do this, and I will have some initial probability, which is my prior probability. Now, before I have started any experiments, I will assume that the coin is honest and it will show the head in exactly half of the experiments. Now I have done one experiment. It showed the head. What do you think? What will be? Now I'm not talking about mathematical formulas, but what will be my intuitive belief that about this probability? What would you say? Say 1/2? Would everybody agree that it is 1/2 after one trial? Yes? Okay, that's fine with me. Now I do another experiment. I get head again. How about now? Are you prepared to change? Now, I mean, 2 experiments. Are you prepared to change your belief? Huh? No. You have an honest coin. You flip it twice. It may show 2 heads. Why not? So no change. Okay, and then we go on. We make 10 experiments, and 10 times we get the head. So now, how about now? Is there anybody who would be prepared now to start thinking about maybe it is a little more than 1/2? Yes? Because the probability of such a sequence to happen is, well, 1 in 1,000 for an honest coin. Okay, maybe a little more. Like, how much more? 0.8? Maybe 0.6. And it goes on. Here we have 20. 20 times, how about now? 1. All right, so we are getting close. Maybe 0.9. We give it a little bit of chance still to be honest. Okay. Now that's the story. This is how Bayesian method of probability estimating works. You start with some prior belief, a priori probability. You perform experiments. You get results of these experiments, and then you update your prior belief. And later I will show you some formulas for updating, but this was intuition. And that method works more or less according to intuition. Now, suppose I have another domain, the mushroom domain. Now I'm in another world. So we are on another planet, Mars, but I'm using Mars for just another planet very far, very different from Earth. We are short of food. We see some plants, some mushrooms there, and okay, the idea is it's very tempting. If these mushrooms turn out to be edible, then we have solved our problem with food. If they are poisonous, then we haven't solved that problem. We like to estimate the probability of these mushrooms being poisonous or edible. Fortunately, we don't have to eat these mushrooms immediately, but we have some dogs in our expedition, so maybe we'll try this on a dog. We do the same thing as here. And now, a priori probability, in the case of the coin, this was very straightforward. But how about these mushrooms? What would you say should the a priori probability be? Well, really, we have no idea. So maybe, since we don't have any idea, maybe we just put it 1/2. Complete lack of information. But notice, this 1/2 is a kind of different from this one. Here, we very strongly believe that the probability is 1/2. Here, this is a kind of out of desperation, of lack of total evidence. Now we take one dog. The dog eats the mushroom, and the dog dies. And we are measuring the probability of that the mushrooms are poisonous. So now we started with 1/2. What would you say now? Shall we do it the same way as here? We'll keep it 1/2 for a while. So we have the 6 dogs. Okay, well, maybe you don't know it, but will you be still sure that it is 1/2? I mean, in the case of coin, you were very sure. After one trial, it is still 1/2. But with this one dog gone, you would be. I mean, I would say this is maybe now 0.75 or something like that. Maybe take halfway to the extreme. But surely I would not leave it 0.5. Okay, then this is not conclusive. I will decide to use another dog. Dog takes mushroom and dies. So now, what will we do with this? One will probably something like that. We are getting fed up with this. We are wasting dogs. It doesn't look nice, and also these mushrooms probably are just useless. So it would be. We'll probably say it's not worth doing more, spending more dogs on this. And yeah, it would be better to eat dogs than hope to. All right, so we have 2 similar situations. Again, probability of the head. We started with 1/2. Probability of poisonous mushroom starting with 1/2. But this column is completely different from that one. So what is the difference? Are we missing something here? What's the difference between these 2 domains? Okay, we're not expert there. That's very good. So we are not really certain about this, and therefore the appropriate setting is the following. Instead of just saying that the prior probability is 1/2, we also need to consider the distribution of this probability. How likely it is that the prior probability is 1/2 or 0.4 or 0.3 and so on. So we use the following plot. That is the probability that we want to estimate. And this is how likely this, so that's PA, how likely particular values of PA are. And for the dogs, for the coins, that was the interesting value. And what do you think? This is the most likely. It's most likely to be 1/2, more likely than 0.25, and so on. So what would be the shape of this? This is now the probability density. It's called a probability distribution. What should be the shape of this distribution? Like, would say like that? No? Okay. Okay. Gauss, so you mean something like that? Yeah. And maybe even more extreme for the coin. So something like something really narrow. We are very sure about the 1/2, and we believe very unlikely anything else but 1/2. Now for the so that's for the coins. Now how about the mushrooms? Maybe flat, because we really have no idea, so we may express our total ignorance by allowing everything equally likely. Yeah? So that would be uniform. Okay, so that is the we're on the right way. In fact, this is how this may work, and Bayesian procedure for estimating probabilities uses exactly this approach. And one particular, if we use this uniform prior distribution, what we get is exactly Laplace estimate. We would still need to do a lot of work, mathematical work, using Bayes formula and integration, a lot of integration, complicated stuff. But in the end, it will all boil down to the Laplace formula. If we and this is a special case of these distributions. We can also have this shape of distributions. So among others, also concave shapes. And then this mathematical procedure with Bayesian updates and so on, and a lot of integration, very complicated stuff, leads to the M estimate formula. And M actually here shows corresponds to the shape of this distribution. For big M, we get these very extreme distributions. And this is for M equals 2, or M equals the number of classes. And this is for M very small, smaller than 1. Okay, so this is how I have connected. Maybe we'll not, I overstepped this. I will not go through all that, these formulas and Bayes updates. And then we have these beta distributions also have a role to play here. Beta distributions are mathematical formulas that correspond to these shapes. And they are often used only because they have a nice mathematical property that when you update a beta distribution with Bayes update, you again get a beta distribution with different parameters, but it is the same. You stay within the same family of mathematical formulas. Okay, we are not going to go into all that, but in the end, we have these formulas that are used that are very useful in machine learning, including tree pruning. Okay, you see, I got to my favorite topic, using domain knowledge, but I got to this a bit too late, so in the end I will not be able to do anything with it. Maybe I can just tell you, I'll just give you one example. suppose that we have this situation here. We have a container filled with water and open drain, and we are observing this outflow. In fact, we are also observing the height of the water in the container. So initially, at time equals 0, we start with this height of water, and then in time, because the water is going out, the level of water will be decreasing all the time. So pretty straightforward. Now we may now perform several experiments with different initial heights of the water in the container, and then we measure at various time points these various heights, and we get learning data. For example, if the initial outflow is 12.2, we get this behavior of the water level. For initial outflow equal 10, we get this behavior, and so on. So all these data points now form our examples for learning. We would like to learn to predict the level of water for given initial outflow and given some time point later, maybe in 10 seconds. So if we apply to this problem famous and well-known learning methods like M5. M5 is a famous learning method by Quinlan, stands for model trees. Have you heard that? M5 was mentioned in this course. Yes? No. Okay. It's a famous. It builds a kind of regression trees, and they are called model trees. And then you apply the learned regression tree on a new initial outflow. Suppose you want to make prediction what will be the behavior of the level of water when the initial outflow is 7.5, and the predictions generated look like that. So what do you think? Huh? That there are some pretty annoying things here that happen there. Well, basically the water level is negative, which it shouldn't be, and also at some point the water level starts increasing. How can that happen? And we all know that this cannot happen in real life. This is crazy. So now having such predictions that violate the main quantitative principle